Hello everybody, welcome back to part 9 of learning everything we can possibly learn in VisionOS documentation by Apple. Here we're going to go into ARKit and we're going to learn via this sample code called HappyBeam. So make sure you download that code and let's go through this together. Leverage a full space to create a fun game using ARKit. In VisionOS, you can create a fun, dynamic games and apps using several different frameworks to create new kinds of spatial experiences: RealityKit, ARKit, SwiftUI, and group activities. This sample introduces HappyBeam, a game where you and your friends can hop on a FaceTime call and play together. You'll learn the mechanics of the game where grumpy clouds float around in the space, and people play by making heart shapes with their hands to project the beam. People aim the beam at the clouds to cheer them up, and a score counter keeps track of how well each player does cheering up the clouds. Here we have a little demo here, and we can watch them play using the Vision developer kit, Vision Pro, and they can make hands. Of course, we currently only have a simulator, so we'll be playing this game in a little different fashion. I think the game here is almost up. Let's pull up our own and let's see how that goes. Here we have loaded up in the simulator HappyBeam. Let's play a solo game. Here we see that we have a little different object here. This is a little point and shoot type of object that we have. It's not the same as the hands, but let's attempt to play this game the best we can without the hands. It's a little bit finicky, and as you can see, this is not easy to do. But I think we're coming pretty close to the end of this game. As you can see, we have this really cool beam that we're shooting out of this cannon, and we're making these clouds really happy. And with that, let's go back to the main menu and let's follow up with the documentation. Design the game interface in SwiftUI. Most apps in VisionOS launches as a window to open up different scenes types depending on the need of the app. Here you'll see how HappyBeam presents a fun interface to people by using several SwiftUI views that display a welcome screen, a coaching window screen that gives instructions, a scoreboard, and a game ending screen. Here's the welcome window. Here comes the instruction screen, the scoreboard, and we have the ending window. So these are 4 different types of windows that we will be using. The following shows you the primary view in the app and displays each phase of the game. Here we have an environment that we will be opening, the immersive space. We have the game model, a session, a timer, and some subscriptions. And here we have a game state, game screen from the game model. And based on the screen states, we send it to a different function and we produce a different type of screen. Let's dig deeper and see what that looks like. Okay, here we have the HappyBeam view, and here it's the exact same code. Let's take a look at what this game state does for us. I think it pulls in the enum and produces an enum. Let's see. Okay, that's strange. Let's pull that away. So this is part of the game screen. Game screen is an enum, and it has a static function where from the states of the game model, based on the game model, we can determine which state we're in and what sort of screen we should display. Let's see what happens when we hit the start. What is start? Let's take a look at that. This is a start view. This is the start view that we'll present. And this will be, I think, the first screen that we see. Cheer up the grumpy clouds by shining a happy beam of your heart, and so on and so forth. There's also the start a SharePlay. session, which is probably not available for us where it's disabled. Um, with that, I think we're pretty clear about how this code works, and let's move on. When 3D content starts to appear, the game opens an immersive space to present content outside of the main window and in a person's surrounding. Here we have our Happy Bee map and game mode, immersion state. We have it as currently mixed. Here's our window group, environmental game model, Happy Beam. And now we have our immersive space with the ID Happy Beam, which generates a Happy Beam space with this particular hard gesture model and our game model for this environment. This has immersion style of mixed, and that's why we have both the outside world and our virtual objects. The Happy Beam container view declares a dependency on open immersive space. It later uses the dependency to open a space from the app declaration when it's time to show a 3D content. If game mode countdown equals 0, then open immersive space. Let's see that in our code. Let's write down this piece of code where we open the immersive space, Happy Beam, and it is when the game mode is 0. Then we will have the game begin and we will open the immersive space here. And the game mode will count down by -1 as this continues. Okay, with that, I think that is our piece of code that we needed to see. And let's keep moving on. Let's detect a hard gesture with ARKit. The Happy Beam app recognizes the central heart shape hand gesture using ARKit support for 3D hand tracking in VisionOS. Using hand tracking requires a running session and authorization from the wearer. It uses the NS hand tracking usage description user info key to explain to players why the app requests permission for hand tracking. Here we have a task, the do try await session.run, hand provider catch AR session error. Hand tracking data isn't available when your app is only displaying a window or volume. Instead, it's available when you present an immersive space, as in the previous example. You can detect gestures using ARKit data with a level of accuracy that depends on your use case and intended experience. For example, Happy Beam could require strict positioning of finger joints to closely resemble a heart shape. Instead, however, it prompts people to make a heart shape and uses a heuristic to indicate when the gesture is close enough. The following checks whether a person's thumb and index finger are almost touching. Get the position of all the joints in world coordinates. Here we have the origin from the left hand, thumb, knuckle, transform, and using the left hand anchor, that origin, transform, and left hand knuckle, thumb knuckle, anchor from the joint transform, get the column number 3 of X, Y, and Z. Then get the tip of the hand. Next, get the left hand index fingertip, and then right hand thumb tip, and index finger tip. And then once you get all of those, and then you get the distance between the two, if the distance is within less than 0.04 centimeters together, then it is a heart shape. Otherwise, it's not a heart shape. So computes a position in the middle of the general heart shape. So get that position is halfway. We get the midpoint, and then we compute the vector using from the left thumb knuckle to right thumb knuckle to normalize the x-axis. And then we have the y-axis from the right index finger, right thumb tip to the right index finger. That'll be our y. And our z is the cross between the x and the y. Then we'll create the final transform to create 3 axes to create a midpoint vector. And there we can return the midpoint. Support several kinds of inputs. To support accessibility features and general user preferences, include multiple kinds of inputs in an app to use hand tracking as one form of input. HappyBeam supports several kinds of inputs. Interactive hand inputs with a custom hard gesture, drag gesture input to rotate the stationary beam on its platform, accessibility components from RealityKit to support custom actions to cheer up clouds, and game controller support to make a control over the beam more interactive from switch control. We have not gotten any code instruction on how to do any of this. Um, well, next, display 3D content with RealityKit. The 3D content in the app comes in the form of assets that you can export from Reality Composer Pro. You place each asset in a reality view that represents your immersive space. The following shows how HappyBeam generates clouds when the game starts, as well as materials for the floor-based beam projector. Because the game uses collision detection to keep score, the beams cheer up grumpy clouds when they collide. You make collision shapes for each model that might be involved. Here we have placements of clouds, and we'll load them from the Reality Composer Pro, from our Cloud Entity bundle. It looks like we do some cloning, and we generate the collision shape and physical body components. Next, we add some accessibility components, the label, the value. It's an elements. It's a button, and it plays a sound. System actions activates, and this is very important to make your game accessible. Lit animation, cloud movement animation. Take the path index, and we play the animation. Next, let's add SharePlay support for multiplayer gaming experience. Use the group activity framework in VisionOS to support SharePlay during a FaceTime call. HappyBeam uses group activities to sync the score, active players list, and the positions of each player's projected beam. Developers using the Apple Vision Pro Developer Kit can test spatial SharePlay experiences on device by installing the personal preview profile. Use a reliable channel to send information that's important to be correct, even if it can be slightly delayed as a result. The following shows how HappyBeam updates the game model score state in response to a score message. Here's the session info with a group session messenger. Reliably, okay. And here's the task where we have a message sender and we're sending information from the game model. Player, filter, ID, and score. Use a unreliable messenger for sending data with low latency requirements. But the delivery model is unreliable. Some message might not make it. HappyBeam uses the unreliable model to send live updates to the position of the beam. When each participant in a call chooses the spatial option in FaceTime. Here we have the unreliable for where the beam placement it will be, and a serial of beam data. So send beam position updates, the 3D pose, and if session equals session, so forth and so forth, we'll send the beam data to everybody. All right, with that, we have walked through the HappyBeam code. We learned how to add SharePlay support for multiplayer gaming experiences. We looked into 3D content with RealityKit, how to add accessibility components and making sure that they're um, uh, cloned and has a collision shape. We also have support several kinds of inputs. This is the meat of it, I think, with detecting a hard gesture of ARKit, how to write code, to look at hand tracking. Lastly, we have this piece of code instructing us how to design the game interface using states and giving us multiple states for multiple views. Lastly, this brings us back to the beginning of our documentation, and that's all we have for Happy Beam.